This is Sparkyville's hydroelectric plant. This is team number 8. I am Levi Seelig.
I'm Juan Cardenas.
Yeah, I'm Venkata Maganti. Yeah, the town of Sparkyville needs more electric power. For this, we prototyped many models and we came with a hydroelectric power plant which can produce a lot more efficient and reliable power compared to the all thermal and compared to the wind energy. We took it since because it's more reliable and it's more cost efficient. For this we have a limited budget and we should be making a mobile model so that should actually be working to present the power output and the sources. And for this we came up with a good hydro power plant which is actually working. For this we have some requirements like the power should be constantly turning and it should give the constant output, and the power plant should be mobile and it should be like fixed in a limited amount of space giving a power output and which has a limited budget of around $50. So we made it more reliable and in the same time we are looking through the budget which is the $50. For that we have gone through many prototypes, and for this we have considered some important steps like limiting the water wastage and conserving the electricity and all.
So this is our final materials listing, and as you can see, our ending budget ended up being $40. So that's about $10 under the Sparkyville budget, and under our projected budget, which was good for both. And just some key features of our materials is that we have the ball bearings for the axle to go into so that it doesn't create friction when the axle spins.
Hi, so my name is Kenny Kerman. So we created a decision matrix for our designs, and we had 5 designs on the table, and these were some of the alternate designs that we had. So for our decision matrix, we chose 5 criteria. We chose their weights based on how much they would impact our final score. So for us, the most important thing was power output, then durability and cost. Aesthetic and originality were just minor side things. So the design we ended up going with was design number 5, with a bigger wheel on top, a smaller wheel on bottom, 6 compartments on the top wheel and 4 on the bottom, because we felt that this would maximize power output in particular, and also durability and originality.
So some important facts about our project were that we have dual wheels, which means that we have two wheels, one on top and one on the bottom. Of course, the one on the top is a lot bigger than the one on the bottom. And what we decided to do was we try to make the big wheel large enough for like when testing comes, like we won't have to be dependent on whether it's high stream or low stream. So we just decided to range it from 5 to 8 inches, and we decided to make it 8 inches so it covers both streams. So we also decided to protect our mortars with water cups, and we decided to use cups because it was like the cheapest resource. So we decided to do that in order to try to save as much as the budget we can. And we used wheels. We cut our wheels using a laser, and that was very efficient on maximizing our use of our materials, which is also very good. And like Levi said, we used bearings for the axles in order for them not to rotate and like move out of the bearing. And this was our finalized design. We first started with the tank, but we had to throw that idea away because the table didn't let us because we used to have a wheel on the bottom, so we were unable to actually put our structure without holding it, or otherwise it would fall. So we decided to do this design. We had these 2 half-inch plywood 1x1s in order to support the base as much as we can, because we're going to have 2 wheels, one 8-inch and one 4-inch. And we just, since that's going to be heavy enough, we just want to have as much weight over on this side, so we won't have to be worrying about whether when water pours out, our structure falling down.
So this is just a time lapse of our build through pictures that we took. So on March 28th, you can see that we have the the 4 arms built for the axles to attach to and the wheels to spin on. And on April 4th, we attached the wheels and we have them in the axle. And then you can also see that we attach the motors on both sides in order put plastic Dixie cups over them in order to protect them from the water splash, because we realized through tests that grab a lot of water splash. And we created the pulleys and then the wires to the back, so that the wire connecting in the back would be safe from any water.
In this project, actually, we worked about the more ratios in figuring out the stuff for producing the maximum energy to be conserved, so that we just use the bigger tooth to the smaller tooth, and that thing which produce the maximum resultant energy, so that we actually conserve the energy. And like the result here, the gate tooths actually quite helped us to figure out that a bigger working wheel is under the smaller working wheel to produce maximum amount of energy.
Alright, so it was necessary for us to produce a power curve. However, due to time constraints, we weren't able to find the stall torque and the no load speed, which are necessary components of a power curve. However, we know that the power curve is supposed to determine where we can achieve max power with a certain torque and load speed.
And lastly, our predicted final score was 24 for the performance metric, just because we predict that we're going to have a lot of water splash. And then for penalties, we're just going to -3 for water resistance again, and then maybe 2 bonus points for aesthetic and creativity. Thank you for listening.
All right, thanks,